Everybody, welcome back to chemistry, and we're continuing on in chapter 8. And so now the topics I want to cover now are a look into the different kinds of spectra you can get when you energize matter such that it releases electromagnetic radiation. And I want to talk a little bit about how a simple atomic model called the Bohr model explains one particular kind of spectra you get, which is called a line spectra. So before I go into that, let me talk about a little bit of a summary of some of the information that we have received about light at this point in time. So one of the things that we saw is that before 1900, it seemed like all the data available about light could be explained by assuming that light was of a wave character. So we found from 1910 there was actually a couple of pieces of data that could not be explained using light as a wave. Instead, we had to sort of switch our ideas about light to understanding that in certain kinds of experiments, the data for the light is better explained if light is a particle. And so those two pieces of data that we were looking at were blackbody radiation. And so what that was is when you heat up an object so hot that it releases a lot of electromagnetic radiation, and a lot of that can be released in the visible range, and so you can see that. And if we look at that spectrum, what the scientists found at the time is that that particular spectrum could not be explained by assuming light is traveling in a wave, but instead light is traveling in a particle. The other piece of data that was found that suggested that light was traveling in a particle was something called the photoelectric effect. And so what that was is where you have light rays striking a metal surface, and then the light rays can, under certain circumstances, release electrons from the surface and they shoot out. And what we learned is that you need light of a particular energy to release electrons from the surface of the metal, and that is best explained by assuming that depending on the frequency of the light you have, the light is traveling as a particle. We pretty much had to throw out the idea at this time that all properties of light can be explained by assuming light is a wave. So now what we sort of say today about light is that we say light has both wave and particle-like properties. And if you want to break this down a little bit more specifically, what we would say is that when we are doing experiments with light, we can sort of understand the data best by working with the assumption that light is a wave. But there are several experiments that we can do with light where if we assume light is a wave, it does not well explain the data. However, when we, for those particular experiments, assume that light is a particle, it does well explain the data. So now what I want to talk a little bit about is I want to dig a little bit deeper onto how particles of light or photons are created by atoms. And so before I do that, what we're going to do is examine some spectra that get released from matter and from atoms. And then after we look at that, we'll take a look at a model that explains how light is released from atoms in the form of photons. Okay, so the first thing I need to do is talk about maybe some of the different kinds of spectra that you can see when you're looking at energized matter. So there's really not a great description of this in your book. So a lot of this information I'm getting from another textbook, which is called OpenStax. It's an online textbook. And if you click on that link there, that should give you sort of a nice description of what I'm going to be talking about. Okay, so when we energize some kind of material, and we can energizing it by heating it, making it super hot, so hot that it glows and it produces blackbody radiation, or if we send electricity through it, what will happen in both cases is that you'll have electromagnetic radiation that is released from these objects. A lot of times this radiation will be released in the visible range that you can see. So there are kinds of spectra that you can get from these objects. And so one particular kind of spectra that you get when you get matter hot enough that it glows and is producing blackbody radiation, if you look at that spectra, what you'll see, it is a continuous smear of color when you're looking at the visible regions. And so if you start out at the red, and then you can just clearly see is that you're getting all kinds of wavelengths going through the colors as you decrease in wavelength going to orange, yellow, green, blue, violet, but as you increase in frequency. So again, this is just a continuous smear of color or wavelengths that you get. When you get this sort of continuous smear of wavelengths, this is called a continuous spectra. Now, you typically get this from objects that are releasing black body radiation. In other words, the objects that are getting so hot that they're releasing electromagnetic radiation over a spectrum of wavelengths. Now, there are a couple of sources of black body radiation that we see in everyday life. So, for example, when you look at the sun is about 5,000 degrees Celsius, at least on the surface of the sun. And so what is going on there is that the sun's molecules, which are mostly hydrogen and helium, are vibrating like crazy. And they're very, very hot, and they're releasing electromagnetic radiation, and you're going to get a very broad spectrum of radiation that is through the microwave, the infrared, the visible, and a little bit into the ultraviolet. But if you were to look at the visible portion of that, it would look like that continuous spectrum that we see there. Another source of black body radiation, which you might see in everyday light, are the old incandescent light bulbs that we used to use before we started using the new ones. And so the way they work is that you have a bulb and you have a very thin filament made of tungsten. And so the way they worked is that you sent electricity through that thin tungsten filament, and that filament would get very, very hot, maybe up to 4,000 or 5,000 degrees Celsius. And it as well would be so hot that the molecules of tungsten would be vibrating like crazy, and they would be releasing a spectrum of color, and it would appear to you, because it's all smeared together into your eye, as white. And so those are examples of continuous spectra that could be produced. However, there's another different kind of spectra that can be made by matter. So this kind of spectra is made when you take purified elements and you stick them into some kind of glass tube and you send a very strong voltage through them. When you do that, you will strike these elements in the glass tube with the voltage, and then they will produce as well electromagnetic radiation. But what you get is not a smear of color like you see with the continuous spectrum. Instead, you get only individual discrete wavelengths that are released by these elements. And so here we have an example of helium. And so you have a glass tube full of helium and you send electricity through it. It will release radiation, but you'll note, again, it's not a continuous smear of color. It's just at these very discrete wavelengths. And so I see one in the deep red, the light red, a pretty strong one in the yellow, another band in green, and a couple of bands in the blue. Obviously, when we're getting this specific line spectrum of helium, it cannot be explained by black body radiation, because black body radiation is going to give you a smear of color. So how is it that we are going to get this line spectra with elements? Okay, so before we talk about that, one thing I want to kind of mention is how you go about seeing this particular line spectra. So I have this sort of set up there in that picture on the right. And so what you will have is you'll have a gas like helium, like we saw before, but in this case, it's actually hydrogen gas that's in the glass tube. The glass tube has electrodes on the end, and you send a very strong voltage between the electrodes such that the electricity that's passing through the glass tube strikes the hydrogen atoms. And when that happens, the hydrogen atoms get energized and they release energy. But as you saw, because it's a purified element, they only release specific wavelengths of energy. So how is that seen? Well, if you were to look at this hydrogen in this glass tube, what you would see is sort of glowing kind of a pinkish purplish color. And what you can do is you can send that through a prism there that I have in that picture, and the prism will separate that color into the individual wavelengths that make up that color so that it appears pink to you. And so one of the wavelengths, one of the colors that is being produced is a line in the red end of the spectra. And so I have that on the bottom there, and you see one of the lines produced is the hydrogen alpha line, which is at 656 nanometers. You can look a little bit further down the spectrum and you can see sort of a bluish green line of emission that is produced. This is about at 488 nanometers. This is the hydrogen beta line. And then there are two additional lines in the violet that are also produced. Now, when you're looking at this spectra, something to keep in mind is that we're only at this particular drawing or experiment looking at the visible wavelengths of light, but it is entirely possible that other wavelengths are being produced in areas that you cannot see with your eye. So in fact, when you electrify hydrogen gas, you will get a variety of individual emission lines, for example, in the ultraviolet range, and also you'll get some in the infrared range as well. So just keep in mind that with this picture, this is not showing you all the kinds of emitted lines of radiation you can get from hydrogen gas when it's electrified. Okay, so one kind of cool thing you can do is you can identify elements based on the particular kind of emission spectra they produce. Okay, so on this slide, what we have is we have the emission line spectra you get when you apply a high voltage to several different kinds of elements. And what I want you to see is that all these different elements produce different kinds of emission line spectra. So what the cool thing is that you can actually identify elements based on exactly the wavelengths that these emission lines are being produced. So for example, we can sort of look at hydrogen here, which we just kind of looked at. And so the hydrogen spectra we see here on this chart is pretty much what we saw before, but it's kind of in the reverse direction. So the red line is here, and then we have the sort of the bluish green line there, and then the two violet lines on the right there. But you can see that there are other elements that produce completely different kinds of spectrum. So let's pay attention to sodium here. So sodium, very interesting. You have some lines, but there are these two major lines that appear to be in the orange-yellow portion of the spectrum. Now, what we can do is sort of relate this to something that we see in everyday life. And so when it gets dark at night, you'll probably notice is that there are overhead lights that turn on. And so you'll probably notice that some of the overhead lights are kind of orange in color and others are in blue in color. Well, the ones in orange in color are, you have a sample of sodium in those lamps that is being electrified. And then what's going on is that the sodium atoms, as I'll explain in a bit, are releasing those electromagnetic radiations in the yellow range that we see here. And so it's those specific bands that are being produced by those lamps. Is that what you're seeing? And so those lamps are called sodium vapor lamps. Now, as I kind of indicated, that there are some light sources outside at night which don't appear orange, they appear more bluish. And so that is due to mercury vapors lamps. And so here in mercury vapors lamps, what you're doing is you're electrifying samples of mercury. And so when you do that, the samples of mercury are releasing specific wavelengths of electromagnetic radiation. You can see of mercury, there's a pretty broad spread of radiation that you can get. There's several lines in the red, orange, and yellow, green, and purple. But when all those lines smear together so that you see them when you're looking at them with your eye, it'll sort of appear a blue color. And so you can see other things as well. For example, neon here. So you might recall neon signs, and neon signs appear red. And the reason is, what a neon sign is a long glass tube with electrodes on the end, and you have a sample of neon in the glass. And so you electrify that sample of neon, and it produces discrete wavelengths of radiation. And so you see a lot of bands there that neon produces. But in the end, what it'll do is it'll all kind of smear together your eye, and it'll appear red. So the next thing I want to get into right now is just try to explain, why is it when you have purified atoms or elements and you hit them with a lot of electricity or heat, they produce those particular line spectra of electromagnetic radiation? And so to understand why this happens, we can use a simple model that was developed around the beginning of the 20th century. It's called the Bohr model. So I want to talk a little bit about the Bohr model. Niels Bohr was a physicist that went to England in 1913, and he sort of developed this pretty simple model of the atom that helps explain how it could be that when you electrify atoms or heat them up, they can release radiation of very specific wavelengths. Now, the prior model before that was the Rutherford model, which we talked about in first semester chemistry. And so the Rutherford model was a pretty simple model. It just basically said that there was a very dense nucleus at the center of the atom and there were electrons surrounding it, but it didn't really give any detail as to what the electrons were doing or were around the atom. But the Bohr model was different. Niels Bohr gave some specific ideas of where the electrons are going to be around the atom, how they're moving, and the energies that they have. So I want to talk about that in just a moment. But one sort of important idea that you'll see with the Bohr model is that with the Bohr model, let's take hydrogen as an example. You know that hydrogen has one proton and one electron. And what you'll see is that that one electron in the Bohr model can be at varying distances from the nucleus. Now, the thing is, it can only be at very specific distances. It can't be at any old distance. And because of that, Bohr said that that electron, because it can only be certain distances away from the nucleus, will give it very specific energies in those locations. And he said that the electron location and the energy in hydrogen was said to be quantized. Now, one of the things we'll also see about the Bohr model is he predicted that you had electrons that were certain distances away from the nucleus that were traveling around the nucleus in circular orbits. What that means is if something is traveling around an orbit, you can sort of know the next second exactly where it's going to be in the orbit. And then you can just continually following the path because it's in a very defined path. Now, this is classical mechanics or physics applied to the atom, where you have particles like electrons. They have very specific trajectories around that they move in, and so you can predict exactly where they're going to be the next moment with just simple physical laws. But one of the things you'll have to keep in mind as we're going through this model is we now know for a fact that electron motion is different. Electrons do not follow trajectories and orbits. Instead, they move around the atom in a completely different way. And so we'll talk about this a little bit later. Okay, so here is sort of the model of hydrogen as Bohr thought of it. And so you can sort of see the nucleus of the hydrogen atom. And you know that in the nucleus of the hydrogen atom, there is one proton. And so hydrogen also has one electron. So the question is, where is this one electron in the hydrogen atom? Is it a specific distance away from the hydrogen atom? And the answer is yes. But the thing is, it can be at different distances away. Now, most of the time, under most conditions, the electron of hydrogen will be in a orbit that is closest to the nucleus. And so I designated that orbit as E1. Now, under other conditions, maybe, for example, if you electrify the hydrogen atoms, you can knock that electron up to another orbit. Here I've designated one as E2. And the E2 orbit, as you'll learn, has a higher energy to it. And when the electron goes up into that higher energy orbital, the electron will have a higher energy as well. And also there is a third orbit there that the electron can get into if given enough energy. And then there are other orbits as well beyond the third. There are 4, 5, 6, and it just goes on up to infinity. Now, one thing to sort of point out in this picture, that the electron can be found in these particular orbits, but you cannot find an electron, say, in between any of these orbits. So like, for example, you never could find an electron in this position here between orbit 1 and orbit 2. And so because you could not find the electron there in between these orbits, he said that the energies of the electrons in these particular orbits were quantized. Another important sort of idea of the model was, now classical physics predicted that when you have an electron which is charged, which is orbiting around a positively charged nucleus, in theory there should be a strong force between that electron and the proton. And electron is not going terribly fast. It's going at some speed, but it's not going terribly fast. And so the classical prediction is that that electron would eventually leave the orbit and spiral down into the nucleus. And as it was doing this, it would release radiation. What Bohr said is that just so that we can have a model that fits the data, we will assume that that is not happening. That in fact, the electron, for whatever reason, even though it's negatively charged and the nucleus is positively charged, for whatever reason, that electron is going to stay in that orbit. And so because the electron was not spiraling down into the nucleus and it seemed to be in a stable orbit around the nucleus, he called that orbit and all the other orbits that the electron could be in, he called them stationary states. Another thing that he kind of pointed out was, again, as I was sort of saying earlier, because the orbits have higher energies as you go further out from the nucleus. We're going to call these orbits something else as well. We're going to call them energy levels. And so when you're looking at the E1 orbit, that is the one that's closest to the nucleus, when an electron is in it, it'll have its lowest energy. You could say additionally, because the electron is part of the atom, that the atom will also have its lowest energy. He said that particular orbit was the first energy level. Now, if for some reason you were able to knock the electron into the second orbit, it would have a higher energy. And you can say in general that the atom, if the electron is in the second orbit, also has a higher energy. And then if it was in that orbit, then that electron would be in the second energy level, and so on. Now, one of the things that you'll have to maybe do on a worksheet or perhaps on a test is actually figure out the energy in joules that the electron or the hydrogen atom has when that electron is in a particular orbit. So there's an equation there that allows you to do that. And so it's a pretty simple equation in that the energy of the electron or the atom on the whole, if you want to call it that, when the electron is in a particular orbit, n being the orbit, is going to be equal to negative RH. RH is a constant called the Rydberg constant times 1 divided by the number of the orbits squared. And so we will give you on your test what the value of the Rydberg constant is 2.18 times 10 to the negative 18 joules. And so one of the things you may be able to see is that when you have increasing orbits going from 1 to 2 to 3, then that n value in the denominator will get larger and larger and larger. And so the value of E will get smaller and smaller and smaller. But because you have a negative sign there, that's going to switch the smaller and smaller energy to larger and larger and larger amounts of energy as the electron goes into higher orbits. And we'll talk more about that in a bit. So again, I'm just kind of pointing out there some of the things I previously said, and so we'll move on. Okay, so here I have a problem that I want to go over, is find the energy of the hydrogen atom when its electron occupies the first, second, and third principal energy levels using this equation. So I'm going to go to the glass board here and try to explain this a little bit. Okay, so let me draw a quick picture of how Bohr thought of the hydrogen atom. So we have a nucleus here, and so to indicate that it has a proton there, I'm going to be putting a positive charge there. And so here is the first orbit that an electron could be in. We'll call this E1. And then we have a second orbit here, E2, and a second orbit here. We don't have to worry about the top part, E3. Okay, and so you probably already know that the electron could also assume orbits that are further and further away from the nucleus, but we're going to ignore those. Now, what I want to do is calculate in joules, if you have an electron, say, in the first orbit here, what will be the energy in joules of that electron? And we can also say that that would be the energy of the entire hydrogen atom for these kinds of problems. So what I'm going to do is I'm going to solve this here. Okay, and so we have electron in the first energy level. So if you were asked to solve this, you will hopefully remember this equation, which is the energy of the electron when it's in a particular orbit defined by the letter n is equal to negative RH and then 1 over n squared. And so you can sort of go ahead and calculate this, and I'll go ahead and do that. So we're trying to find again the energy the electron has when it's in the first orbit, which is closest to the nucleus. And so it's going to be negative 2.18 times 10 to the negative 18 joules. And then it's going to be 1 over 1 squared. And so you can sort of see that work out, that the energy that the electron has actually has a negative number and a very small exponent. It's negative 2.18 times 10 to the negative 18 joules. Okay, now I've been saying that the electron, if it's for some reason bumped out into a higher orbit, it will need energy for that to happen. And because you need energy, because when the electron goes out to this higher orbit, it will have higher energy once it's in that orbit. So you can actually do this calculation for the electron in the second orbit, and so it would be negative 2.18 times 10 to the negative 18 joules, and then it's going to be 1 over 2 squared, and you can actually work that out, and the number you get is negative 5.45 times 10 to the negative 18 joules. Okay, so that would be the energy of the electron if it's in the second orbit of hydrogen, or the total energy of the atom. And so you can calculate it for the third, and you kind of do it in the same way. Negative 2.18 times 10 to the negative 18 joules times 1 over 3 squared. And then you can sort of work that out. And so I think I have the answer there, which is negative 2.42 times 10 to the negative 19. Whoops. So actually, going back to the energy of the electron in the second orbit, I should have changed that to negative 19. Now we're fixed. Okay. So now I want to take a moment to sort of explain why. How could it be that we have these unusual numbers for energies and that they're negative, number one, and the exponents seem to be getting smaller and smaller. And yet at the same time, I'm saying that the energy of the electron is getting greater and greater as it goes out into higher and higher orbits. And so how could that be? So I sort of have a diagram of that idea there on the screen there. And so there I'm looking at, on the y-axis, the relative level of energy that an electron can have. And what you can see is at the very bottom, that purple line, that is, again, the energy we just calculated that the electron will have when it occupies the first orbit. So that's negative 2.18 times 10 to the negative 18 joules. Now, when we push the electron into the second orbit, it gets a new value, which is negative 5.45 times 10 to the negative 19 joules. And as I'm going to show you in a minute, that's actually a higher amount of energy. When you go to the third orbit, which is negative 2.42 times 10 to the negative 19 joules, that's even higher energy. And so if you wanted to, you could push up the electron to orbits that are further out, and then they will have higher and higher energy. But there will be a point where, as you can see, those energy levels are sort of collapsing into one another. They're getting asymptotic. And so maybe when you have like the electron out to, say, a orbit that's very far away from the nucleus, and you're pushing the electron maybe to one more out from that location, there will be very little energy change. And so any energy added to the electron will probably be just enough at that point to completely shove it off the atom. So let's go back and take a moment to try to understand, how could it be that when you're going into more negative exponents, we're actually increasing the energy of the electron or the atom? So here's sort of the way I think about it on the glass board. So think of a number line. So we have a number line here, and so the number line, I'm going to put a 0 here, and then we have a positive 1, and a positive 2, and a positive 3, etc. And here we have negative 1, negative 2, negative 3. All I'm going to do with this number line is I'm just going to turn it 90 degrees, and we're going to look at it in a different way. But one of the things you can sort of understand already is that as you go up in the number line, the numbers are just getting larger and larger and larger. So let me just kind of flip this over like this. So we have 0 here, negative 2, negative 3. So as I was kind of saying, as we know that the numbers are getting larger and larger and larger as you're going up the axis. And so we can sort of think of this also as an axis of energy. So if you can go up this axis to higher and higher values, that indicates that that thing whose energy you're measuring is getting greater and greater energy. So let's kind of map out where these energies of the electrons would be when they're in their particular orbits on this number line. So for example, when the electron is in its first orbit, it has an energy of negative 2.18 times 10 to the negative 18 joules. So here I'm going to map this, and so I'm not going to use the exact correct location, but what you can see is because the exponent is negative 18, it's going to be a negative here because of the negative sign. 0.000, and there will be, I think, 17 zeros followed by a 218. So it's a very small number. So we'll just put this here. So this energy when the electron is in the first orbit is negative 2.18 times 10 to the negative 18 joules. Okay, now let's think about where the energy would be when the electron is in the second orbit. And so I kind of corrected this down here. When it's in the second orbit, the energy of the electron is negative 5.45 times 10 to the negative 19. So where would that be on the number line? Well, here we have times 10 to the negative 18. Times 10 to the negative 19 should be even closer to 0. So I'm going to put this here. It's going to be closer to 0. So this is n is equal to 2. And so this is negative 5.45 times 10 to the negative 19 joules. And so the next one, n is equal to 3, is going to be even closer to 0. So what you can sort of see is that as the electron goes out into higher orbits, those numbers are actually greater and greater energies. And what is also true for the electron is going to be true for the atom as a whole. And so basically, when you have very negative numbers here on the number line, this is low energy. And if you have very positive numbers on this number line, it's very high energy. And one of the things you'll learn about probably later is that if you have a system in chemistry that has relatively low energy, it's said to be relatively stable. And if you have a system that has relatively high energy, it's relatively unstable. So as we shove this electron into orbits that are further and further away from the nucleus, going from n equals 1 to n equals 2, n equals 3, that electron and the atom will have higher and higher energy, and it will be said to be more unstable. So what does that make this first orbit here? This makes the first orbit of hydrogen to be the location where the electron can be, where the hydrogen is in its most stable state. And so when the electron is in the first orbit, then hydrogen is said to have an electron in the first orbit, and then this state, when the electron is in the first orbit, is called the ground state. Furthermore, if the electron is shoved up to orbits that are further and further away with higher energy, then you would say that the electron and the atom on the whole will be in an excited state. And so if the electron is not in the first orbit, but it's in the second orbit, the third orbit, or more orbits further out, then you would say that the hydrogen is in the excited state. And then because of that, it has more energy and is more unstable. Okay, so let's move on. Okay.